Chapter 25 will show us another set of hypothesis tests and confidence intervals. Anytime we've had two samples up to this point, we've been stating that the samples are independent of one another. In this chapter, we'll be talking about specific situations where they're not independent of one another. The inference methods we'll be conducting in this chapter have to do with paired data. It's when observations are collected together and one group is naturally related to the other group. Say, for example, we went to 50 couples and we asked both the husband and the wife, how much TV do you watch per week? If the husband watches an above average amount of TV, it becomes likely that the wife also watches an above average amount of TV. The two responses are not independent. Compare that to asking 50 randomly selected men and 50 randomly selected women that same question, and we'll have different differences among independent samples than we would in a paired sample like husbands and wives. So there are certain relationships that result in paired data like married couples, brothers and sisters, etc. But most commonly, we'll have two readings on the same subject before and after a treatment is administered. When we have paired data, we actually don't care about the original data. All we care about is how much it's changing both before and after that treatment, or what's the difference between each individual husband and wife, etc. Since we only care about those differences, we subtract the two samples. Once we subtract them, we throw out those two samples and we're only looking at those subtracted values. It becomes a one sample t-test like we did in chapter 23. So a paired t-test is the same as a one sample t-test, only we're just looking at the difference of those two samples that we started with. The sample size is the number of pairs. Assumptions and conditions, there's just one thing to note. We have the three standard ones, including nearly normal. Since it's quantitative data, we don't have paired samples with proportions. And then the fourth, anytime we had two samples, we've always been saying these two samples are independent, and that's expressly not the case with these types of problems. The reason we'd be doing a paired test is because the samples are not independent. They are paired with each other, so we subtract them and we look at the differences. Now these equations look different, but it's really just the same thing as we had back in chapter 23. In 23, we did x bar minus mu divided by the standard error. Now we have d bar. D bar is the average of the differences between our two samples. Subtract that null hypothesis value, divide by the standard error. Standard error is standard deviation of those differences divided by radical n. Confidence interval, our point estimate, is the average difference. Margin of error, t-score times the standard error. For example, a health department experimented with a flexible 4-day work week. For a year, the department recorded the mileage by 11 field workers on an ordinary 5-day work week. Then it changed to a flexible 4-day work week and recorded mileage for another year. Did the change in schedule change the mean number of miles driven? So we have our data at the bottom of the slide here. And the first thing we want to do is identify what type of test this is. So we have two samples. It's quantitative data. We only have two options. Either it's a two-sample t-test or it's a paired t-test. I'm also just saying test and not intervals because the question it's asking is a yes or no question. Did the change in schedule change the mean number of miles driven? Yes or no? We solve yes or no problems with a hypothesis test. If it asked us to estimate the change, we would do a confidence interval. Now, we have two readings on each of these employees. Two for Jeff, two for Betty, two for etc. We don't care what the average was before compared to after. What we care about is how much do these change individually. Okay? How much more or less is Jeff driving? How much more or less is Betty driving, etc., etc. So we want to find the difference for all of these individual employees. And that's the parameter we're trying to estimate. Let mu d represent the true mean difference in mileage before and after changing from a 5-day work week to a 4-day work week. And we also want to note how are we subtracting these. So we're going to do before minus after. Now we find the differences and we get this table. And once we have these differences, we can throw away those original two samples. We don't care about them anymore. All we care about is the differences. And since now we only have one sample, this becomes a one sample t-test. Hypotheses. Null hypothesis is that the mean change in mileage is equal to 0. There is no mean change. That's going to be your null hypothesis 99% of the time, although it is possible, depending on the wording, for this to be some number other than 0. Okay, we're saying, did this schedule change the mean number of miles driven? It doesn't say, is it more or less? So we're making an alternative of not equal to 0. Assumptions. All right, so we're saying this is paired data. We have 2 measurements on the same individuals before and after a change in the work schedule. We're going to assume the differences in trips before and after the schedule are representative of all employees. 11 employees is less than 10% of all employees. And we need to check the plot because we don't have enough data to apply the central limit theorem. Here's our normal probability plot. Make sure you draw it. It's reasonably straight with no outliers. Now, I've been saying that this is a one sample t-test, and that's how we're going to actually go through the steps, just the same way we did in chapter 23. But when we name it, we call it a paired t-test. And we have to call it a paired t-test because we started with 2 samples and we're not using both of them. We found the differences, we threw out the original, and now we're just doing the one sample t-test on those differences. Paired t-test is the name. Find the test statistic. We find first all the metrics from one variable stats. That's going to give us an X bar of 982 and a standard deviation in our sample of 1139.6. So standard error is S over radical N, 1139.6 over square root of 11, 343.6. Test statistic, whatever our sample showed, and our sample showed a difference of 982. Subtract the null hypothesis. In almost every case, but not all cases, the null hypothesis is that there's no change. Okay, is that difference unusually large compared to our standard error? We get a t-score of 2.857, 10 degrees of freedom. This is 10 because it's n minus 1, and n is 11. We had 11 employees, we had 11 pairs of data. Now we would go into TCDF. Remember, for a two-tailed test, whatever we get here, okay, so when we do this, we get a 0.0085 for this tail, and since it's a two-tailed test, we have to double it because there are more, it's more area on the other side. Reject the null hypothesis since the p-value is small. There's sufficient evidence to suggest that the mean change in miles driven is different after the work week was changed from 5 days to 4 days. If you're asked to interpret the p-value, if the null hypothesis is true and there is no difference in the mean number of miles driven before and after the schedule change, the probability of seeing an average difference of 982 or more is 0.017. And let's close out the unit with a confidence interval. Estimate the mean change in miles driven. Now it's not asking us a yes or no question. It's asking us to quantify the mean change. This is a confidence interval instead of a hypothesis test. Parameter and assumptions, we already did. Name the method. This is a paired t-interval. Write the interval. Okay, so here's our standard error again. Our d bar was 982. We always start with whatever our sample showed. This is our point estimate. Add and subtract the margin of error. So degrees of freedom was 10. We could look up a t-score. Remember that we always put 90% in the middle here. And then we add in this left tail. So area would be 0.95. We'd go into inverse t. Put in 10 degrees of freedom. That gives us our critical t-score. Margin of error is just that t-score times the standard error. We get an interval of 359.4 to 1604.6. We are 90% confident that the true mean change in miles driven after the schedule is changed to a 4-day work week lies between 359.4 and 1604.6 miles. If you're asked to interpret the confidence level or explain what 90% confidence means, a confidence interval conducted using this method will capture the true mean change in miles driven in approximately 90% of all intervals.